We're now going to introduce product measures. So suppose you have a space X with a sigma algebra S and a positive measure mu, such that X is sigma finite. And you have another space Y with a sigma algebra T and measure lambda, which is also sigma finite. And let Q be an element of the sigma algebra S cross T. Then we can define two new functions. Phi of X is lambda of the X section of Q, and psi of Y is mu of the Y section of Q. For every X and for every Y, so this is an X. Then the theorem we are going to prove is the following. This function phi of X is measurable with respect to S. Phi is measurable with respect to S, and psi is measurable with respect to T. And the integral of phi over X d mu is equal to the integral over Y of psi d lambda. So this is the content of the theorem. Now let's prove it. We are going to call the class of sets such that the content of the theorem is true omega. And we are going to see the following. Every measurable rectangle is an omega. Well, this is easy to see. Suppose you have a measurable rectangle Q. This means there's this rectangle A cross B, where A is a subset in the sigma algebra on X, and B is a subset in the sigma algebra on B. Then we have the following. Lambda of the X section of Q is lambda of b times the characteristic function of a x. This is because the x section of Q is B if X is in Q and is the empty set. If X is not in Q, this we have shown in a previous lecture. And this is the same as lambda B times the characteristic function of A x. And in a similar way, mu of the y section is mu of A times the characteristic function of B y. And if we now integrate this one with respect to mu, and this one with respect to lambda, then we get the same in both cases. In both cases, we get lambda mu of A times lambda B. So both integrals are the same as stated in the theorem, and this proves that the theorem is true for every measurable rectangle. Next, suppose we have an ascending sequence of sets in Q, in omega. So this is a sequence Q1 is a subset of Q2 and so on, such that we have a set Q without index that is the union over all Qi, and these are supposed to be in omega, and we need to prove that Q is in omega too. To check that Q is in omega, define phi I for every I. Phi I of x is lambda of Qi x, and define phi I of y as mu of the y section of Qi. This is Qi, and write phi x is lambda of Q, and without I, phi y is mu of Qy. Then we have an ascending chain. Phi I of x tends to phi of x, and psi I of y tends to psi of y. So using the monotone convergence theorem, we can conclude that the integral over x of phi d mu is the limit of the integrals of the phi I d mu, and we can write a similar equation for psi i's and psi, and thus we can conclude that indeed Q is in omega. Now the next thing to notice is, Suppose you have a countable family of disjoint subsets Qi. So this is our countable family of disjoint subsets Qi, and each Qi is in omega. So each Qi is an element of omega for all I. Then if you look at the union of all Qi's, remember this time we're not necessarily talking about an ascending chain of sets as in the last statement, but these are arbitrary disjoint subsets, which are in omega, of course. Then the union of the Qi is in omega again. Now, to see why this is true, look at it the following way. You can express lambda of Qx as the integral over y of the characteristic function Qx xy dy. And this means that for finite unions of disjoint sets, the statement is clear because the characteristic function of the disjoint union of finitely many disjoint sets is the characteristic function of the union. And now for arbitrary countable unions of disjoint sets in omega, we can apply the statement we have proven a moment ago. We have shown that if we have an ascending chain of nested sets Qi such that every finite union is in Q, then the countable union of the Qi's is in omega, then the countable union of the Qi is in omega. And to apply this to the case of disjoint sets, you just start with one Qi, add another one, and so on, and you get an ascending chain of sets Qi, and then you can apply the statement we have proven a moment ago. Now we need one more statement of this sort. Suppose you have a set A, which is in the sigma algebra S, and such that mu of A is less than infinity, and a set B, which is in the sigma algebra T, such that lambda of B is less than infinity, and such that A cross B contains a set Q1, which contains a set Q2, and so on. And we write Q for the intersection of all Qi. Then we need to show that this Q, which is the intersection, is in omega. Now again, to to every qi, we have, or we can write phi I and psi I, and since this is a descending chain which descends to the intersection of the qi, which is q, we can apply the dominated convergence theorem. This is allowed because mu of a is smaller than infinity and lambda of b is smaller than infinity. So we have that q is in omega by the dominated convergence theorem. And now remember that we said x has to be sigma finite. Here we stated that x is sigma finite. So this means that x is a union of countably many sets which we call xn, and such that mu of xn is less than infinity, and the same for the space y, because we said y is also sigma finite, so y is a countable union of sets yn where every yn has lambda of yn less than infinity. And so now let's use that to write our set, or to write a set Q in S cross T as a union of intersections. Namely, let's call QMN the intersection of Q with XN cross YN. So this XN is one of these sets XN I've just referred to, and we have that Q is the union over the sets QMN, where M and N ranges over all M and N. And these sets QMN are disjoint. So if we can show that QMN is in omega for every Mn, we know that Q is in omega because unions of disjoint sets in omega are in omega, as we have just shown. And this would conclude our proof. So the last thing to do is to show that QMN is indeed in omega. So let's call the family of all Q's such that QMN is in omega for every M and N, big M. And now if you think about it, what we've just seen in the course of this proof is that this class M is a monotone class, and it contains the elementary sets. And we have shown in a previous lecture that the smallest monotone class that contains the elementary sets is the sigma algebra S cross T, So every set Q in the sigma algebra S cross T has the property that QMN is in omega for all M and N. And thus we are finished with our proof. Thank you for watching. See you next time.